Now, when I go inside and want to take the sample gradients, what are the parameters that I'm going to take the gradient with respect to? W and theta, right? W is your encoder parameters. Theta is your decoder parameters, right? So I want to take the gradient with respect to these two parameters, so encoder and decoder. So how can I take the derivative with respect to decoder? Well, I'm going to write down that expression that I have. So this expression is exactly the expression of the risk term. And now I just compute one sample gradient. I take the gradient of this expression with respect to theta. Now, theta is showing up in the first term, right? So I need to compute that gradient. But in the second and third term, that theta does not exist, right? Am I correct? The second and third terms are the terms of KL divergence, right? They only depend on your encoder. They don't care about your decoder, right? The KL divergence is there to make your encoder somehow generate some posterior which is matching the true posterior, right? So this is not going to depend on your decoder. So this gradient is essentially 0, right? So those things disappear. The only thing that remains is this guy. And given that the expectation is taken over the encoder, which does not depend on theta, I can simply take the gradient inside the expectation, right? So gradient of expectation of a fixed distribution is going to be the expectation of the gradient, right? OK, so I'm going to do that. Can I now compute this guy? Is it possible that I compute this guy? What is G here? Is the generator, the network which is generating the mean value, right? It's a neural network. Can I compute the gradient of this term when G is output of a neural network? Yes, I can simply go forward, backward, then I compute the gradient, right? So that guy is easy to compute. This is a simple backpropagation. Essentially, you open it up by chain rule. You're going to say the gradient is going to be the gradient with respect to G times the gradient of G with respect to theta. And that gradient of G with respect to its parameters, you can simply compute by backpropagation, right? So that gradient, the gradient of your risk with respect to decoder, is quite easy to compute. It's the straightforward thing that you always do. Okay? So that is not a problem. Now, let's see how exactly, given that we have this particular expression for R, the risk, which is depending on the expectation over the encoder, let's take a look and see how exactly we can compute it if we are in practice implementing this. So this is not quite a hard thing to do. So essentially what I'm going to do, if I am thinking about one single sample X, right? I have my encoder already there, so Q is already available, right? What I want to compute the gradient with respect to decoder, right? So the thing that I'm going to do, I'm going to sample from that encoder a batch of samples, right? So Z, as you see here, the ZL are n different samples coming all from the encoder, right? That conditional Gaussian distribution, right? So I pass X over my encoder, I get the mean and variance, and I take a bunch of samples, right? Now that I have these samples, now I go inside a loop. For every single of those latent samples, I'm going to pass that sample over the decoder, forward, backward, right? When I go forward, backward, I have the gradient, right, for that particular sample. And I do it for every sample that I have. So essentially, I just pass it forward, backward. I use the chain rule to compute the gradient of that first term that we had, right? And now, once I'm out of the loop, I'm going to average all of those gradients that I computed. And this is going to be the gradient of my risk for the particular sample X. Yeah? So there is a tiny difference here as compared to the classical backpropagation, because in classical backpropagation, your term is is just one term, right? You just get your data sample, you pass it forward, backward, you compute the gradient. Here, you need to do one extra sampling, right? So you need to sample your latent first, and then you pass those samples over decoder to just get the gradient, right? But this is not a big deal. This is just extra computation. Correct? Okay, so that is going to be the gradient with respect to decoder. But what about the encoder? What if I want to take the gradient with respect to encoder? Again, let me write down this expression. So look at this expression here. This is the expression we want to take the gradient with respect to. Okay, this term, these two last terms, they are essentially the gradient computed of some function at the output of the mean and covariance networks, right? So they are essentially neural networks. I am passing x through that, right? I'm going to see at the output of them something, and I can simply use backpropagation to compute the gradient, right? So that is not an issue. These two guys can be simply computed by backpropagation. But what about this guy, the first term? How can I compute the gradient of this guy? If you want to compute the gradient here with respect to w, you cannot simply take this gradient inside the argument, because the thing that is depending on w, on your encoder here, is actually the distribution. It is not the argument, right? So you cannot easily do that, and this is the key challenge here. This is the key difference to the classical backpropagation. So the two last terms, you can simply compute it by classical backpropagation, but this one is not a conventional gradient computation that we had before, right? So the thing that is depending on the parameters is the distribution with respect to which we are computing the expectation, right? So this is the challenge here, and I just want to clarify it for you why this is a challenge, okay? So take a look at this expression. Right now, assume that I'm able to compute the expectation perfectly. So I have this term here, and I take the expectation with respect to some distribution q, which depends on a bunch of parameters, right? And I want to take the gradient with respect to those parameters, right? If you open up this term for expectation, you essentially have the same term that you had before here, times the distribution times dz, and then you take the integral, right? Now, if you want to take the gradient of this expression, you obviously see that that gradient goes inside integral. It's going to take the gradient with respect to q, right? But once it takes the gradient with respect to q, it is not expectation anymore, right? So this is not the classical thing that we had before. And one thing that you should pay attention to, so this gradient simply goes inside this one, right? And now when you look at this one, this is not necessarily an expectation, right? Because the gradient of q is no more a distribution, right? There is no reason for gradient of q to be distribution. Indeed, when w is multidimensional, this is a vector. This is a totally different thing, right? So this expression here is totally different. And one thing that you should very much pay attention is that you cannot simply take the gradient and take it inside the expectation now, right? So if you take that guy inside, like this gradient inside, you are essentially, I mean, if you write down the definition of this guy, this is going to be a totally different thing. It's going to be the gradient of this expression times q, right? Which is not this guy above, right? So gradient is not easily going inside anymore, right? So if you want to take, if you do this, I mean, if you take the gradient and take it inside naively, then you're going to say that, okay, gradient of this term with respect to w is simply 0, because w is not showing up in this expression, and then expectation of 0 is 0, right? But obviously this is wrong, right? Because you know that this expression depends on w. The point that is happening here is that actually this z value that you have here, the sample z, is depending on w, right? Because it's coming from a distribution depending on w. But this is not a kind of, deterministic function of w, right? It's a random function of w, and we don't know exactly how we can take derivative of a random function of some particular variable, right? So everybody's clear why this is challenging? So this is why this is not a classical backpropagation? So the whole challenge is that we want to take the expectation of one random function, and that random function depends on the parameter that we are taking the derivative with respect to, but not in a deterministic form, right? In a stochastic form. So, yeah, this problem is not only showing up here, so it's not like people who develop VAE, they started to come up with a totally new idea. This is actually a kind of old problem. And some of you who have maybe worked with reinforcement learning in policy gradient approaches, you might have seen it as well, that sometimes you need to take the derivative with respect to the distribution of an expectation, right? And there are essentially two different approaches to do that. We're going to just look at it quickly here. Now, let me just simplify the problem so we don't look at that complicated form. Let's say that I have one particular function f. So this function f is a function of one variable z. And that z is a random variable whose distribution depends on w, right? If I compute the expectation of fz, function of that z, if I take this expectation with respect to q, then the argument that I have computed is depending on w, right? And the thing that I want to do is I want to take the gradient of this expression with respect to w, right? This is exactly what we have in our training problem. So if I want to do that, the first trick that we can do, first of all, I can just open up this term, right? So this expectation is essentially the argument f times the distribution times dz. I take the integral, and now this gradient is going to go inside the integral. It can simply pass there, and it's going to be the f times gradient of q times dz, right? So I want to compute that one, but in a computational form, right? There are two different approaches that we can do. The first one is importance sampling, which is the one typically we use it in reinforcement learning because there the distribution is quite general. But sometimes when the distribution is well defined, as we have here, we can do the other trick, which is called reparameterization trick. Okay? So now let's first look at the importance sampling argument. So I want to take, the gradient is of this form, right? Just went inside and took the gradient from q, right? Now, you can use a super easy argument here. So the argument is that the gradient of log of a function is simply the gradient of the function divided by that function, right? Everybody agrees? Gradient of log of anything is the gradient of that thing divided by that thing itself, right? Is log, right? Now, if I take this q, if I multiply both sides by q, what's going to happen? Gradient of q is q itself times the gradient of its log, right? So that's a simple identity, right? So what I'm going to do, I'm going to replace the gradient of q here with this identity. So I am saying that the gradient of q is gradient of log, this term, times the denominator of this guy, which is q, right? Everybody agrees? Yeah? Now, look at this guy. Is this guy something that I can compute? What is it? It's expectation, exactly, right? So if you look at this term, if I factor out this q, whatever is inside the integral except q is going to be the argument of the expectation. And we are happy with expectations because we can just compute them by sampling, right? So this guy is expectation of f times gradient of log of the distribution, right? So gradient can go inside the expectation, but you're going to carry gradient of log with itself, right? And then you can solve the problem. This is quite general for any distribution it's going to work. And this is, again, one important sampling argument, right? If you remember, we had before important sampling that we wanted to take the expectation, but then we played with the distribution, right? We changed the distribution, and we added one argument, which was the important sampling argument. Again, we are doing the same thing here. And this guy, this gradient of log, is eventually the importance sampling argument. Everybody's clear? So if you want to think about it algorithmically, you can simply say that, OK, instead of computing the expectation, what I'm going to do, I'm going to replace it by approximate of the expectation, which means that I'm going to estimate it from samples, right? So I have this argument, which I can compute for every single sample. I just collect a bunch of samples from Q, and then I average this argument over those samples. So you can think of it in this form. So you get a bunch of samples Z for the particular distribution Q. And then for every single Z, you are going to pass this Z over the network, forward and backward. So the network is now essentially a log of your encoder, log of your distribution, right? This is the argument that you want to take the gradient with respect to. And once you have done it, you just simply multiply f of that sample with the backpropagation of that log Q, and then you average it over the samples that you have. Everybody's cool? Yes. Yeah.
Here, the red Z is the x minus the generated output?
X minus the generated output? No. This is Z is is the latent, is the Z inside that generator, right? Right. I'm going to do it again for that argument to see it, but that one you can simply do the do it by. I mean, the point is that this argument that you have, this is not going to do any harm for you, right? The thing that you want to take the gradient with respect to is gradient of the log Q, right? So the guy who you're going to backpropagate is log Q, right? So this argument is going to copy exactly. So as you said, Fz instead of this one, it's going to be that norm of x minus g theta z, right? And then you put the sample inside that argument, exactly. Questions? No question? Great. So now, this was the importance sampling. As I told you, this is a very general approach to just compute the gradient of a stochastic function. But there is also another approach, which we call it reparameterization. So what is the idea here? The idea here is that if we can, if this, I mean, depends on this if, really. If we can present this random variable z that we have as a kind of deterministic function of another random variable whose distribution does not depend on w. If we can do that, then the problem can again be solved easily. So say that I have one epsilon. It depends on distribution q0. q0 does not depend on w. Okay? It's a fixed distribution. Now what I do now is that if I have this epsilon, whose distribution is fixed, if I pass it through one function f, which depends on w, then I'm going to get the sample from the qw. Okay? So my z sample is going to be the processed version of this fixed sample epsilon, right? If I do know that, if I can make this function up, then I can easily compute that gradient. How can I do it? I could say, OK, I want to take the gradient of the expectation of this term with respect to z. But z itself can be written in this form, right? So I can replace, instead of z, this expression. And then instead of doing the expectation with respect to qw, I do it with respect to the fixed distribution q0, right? Everybody agrees? So these two expectations, as long as I can find this function here, are the same, right? But now, can I take the gradient inside in the second expectation? Yes, because q does not depend on w anymore, right? Q depends on nothing. I mean, it's a fixed one, right? Everybody's clear? Right? So I can take that that gradient inside, and now I only need to take the gradient of this expression, which is going to be the gradient of the capital F with respect to its argument times the gradient of its argument, which is this new function I found, with respect to the weights. Right? Everybody's clear? Questions? So this is what we call it reparameterization trick. So you get your random variable, you just write it down or rewrite it with the parameters that you have in a functional form, and then you take the derivative, right? And this is the one which we typically use in VAE, because in VAE we have this particular property, okay? So, yeah, if we want to do the computation with reparameterization, eventually we need to first find this function. So this is important that we are able to find this function. And once we find this function, we can just do one simple backpropagation inside the expectation, and we take the expectation. So this means that if I have this property, then I am going to take a bunch of samples from that fixed distribution Q0, right? A bunch of epsilon samples. And now that I have these samples, now I go inside one loop, and then I just send those samples forward, backward through the network FW. And then I use chain rule to compute the gradient, and then I just average those gradients, right? This is going to be the gradient that I want now. Everybody's cool? Questions? Yeah.
I guess I was wondering, could you explain the reparameterization? Like, what are, like, before we had W as our parameters?
Yes.
What are the new parameters, I guess would be the way to.
We actually don't have new parameters. We just have new functional representation, right? So here, what we had, I mean, this Z is coming from one parameterized distribution, right? But what we know is that if we take samples from non-parameterized distribution, then we can get that sample, and then we just do some deterministic process on it, depending on our parameters, and then we compute the sample from QW, right?
So it's easier because there aren't new parameters.
This is, I mean, you have the same parameters as before, but then they are just showing up inside the argument, right? I think if I give you the example of VAE, then you're going to understand it more clear.
I think so.
Yeah, because in this case, we really have this property. Okay? Questions?